Hello, and thank you for coming to view our poster today, the title of which is Preventing Crystallization with the Crystal 16 for Successful Parenteral Formulations. Many drug substances are formulated as parenteral or liquid formulations, which are directly injected following dilution to the correct concentration. A potential pitfall is precipitation or crystallization in such highly concentrated formulations. These can cause irritation to the recipient, impaired drug performance, and, in some cases, more serious systemic issues. The commercially available lorazepam solution is quite viscous, and therefore dilutions with aqueous sodium chloride or 5% glucose are always prepared before injection. When administered via IV, lorazepam was actually crystallizing at the injection site. Therefore, it was necessary to determine the solid-liquid phase diagram for the lorazepam in mixtures with aqueous glucose solution. In this study, solubility measurements were performed with the Crystal 16 instrument and its transmissive technology. In just 4 hours, we determined complete temperature-dependent solubility curves for lorazepam. Further, the crystallization process of lorazepam could be followed in situ using the crystalline instrument from Technobis and its real-time particle imaging, which works exactly like a microscope. With the crystalline, we were able to observe that lorazepam crystals exhibit an extremely needle-like morphology when formed at or below a concentration of 0.5 milligrams per ml. Interestingly, at higher concentrations, the needles were deformed and strongly curled. These differences indicated that for a 1 milligram per ml solution, the supersaturation for crystallization is much higher than for a 0.5 milligram per ml solution. The phase diagram constructed with data from the Crystal 16 showed that high lorazepam concentrations and low glucose solution volume fractions may lead to a stable solution in which lorazepam crystallization will not occur. This also confirmed that the glucose solution acts as an anti-solvent, reducing the lorazepam solubility in the infusion solution. Technobis crystallization systems are very thankful to Professor Joop ter Horst and his colleagues for providing the content of this poster. We would also like to express thanks to the Royal Society of Chemistry, Formulation Science and Technology Group for allowing us to exhibit this poster at their meeting.
Hello, my name is Claire Pizzi, and thank you for watching my presentation of my poster about particle characterization methods at the Diamond Light Source. Diamond is a UK national research facility focusing on advanced materials characterization. We're funded by the UK government and the Wellcome Trust, the UK's largest biomedical charity. We're essentially not-for-profit. Small angle X-ray scattering is one of the techniques I'd like to talk to you about today. This is a technique where the contrast arises from electron density differences between the particle and the surrounding media. So we can look at a wide range of different sample types. These can be opaque or have non-volatile solvents, so they're very good when other techniques struggle. From this, we can get information about particle size distribution if they're all the same shape, particle shape analysis, and then if they're anisometric, which they have a preferred orientation in a field, for example, or under flow, and we can get information about particle alignment and orientation. An example I'd like to talk to you about is looking at green rust. This is a complex nanoparticulate mineral which forms in wet oxygen-free materials. The study we did here was looking at the kinetics and mechanism of particle nucleation and growth. So you can freeze it at different points and start looking at how this process continues. We also did some work with Hewlett-Packard looking at how pigment dispersions in the liquid crystal matrix were structured. So here the solvent is structured rather than the particulates, but it's quite interesting to understand how these pigments are dispersed across the whole solvent. X-ray absorption spectroscopy is another technique, a group of techniques available at Diamond, which is sensitive to the chemistry of the materials. And here we have the periodic table showing all the elements accessible at Diamond. The example I'd like to show here is looking at nanoparticles formed in tissue from wear metal on metal hip implants. So we did a microfocus spectroscopic mapping to image tissue and find the nanoparticles and their chemical speciation. The last group of techniques I'd like to talk to you about is X-ray imaging. So this is radiography or three-dimensional tomographic imaging, which can be reconstructed to get complex internal structures of materials. We had some work done at the University of Manchester and Unilever looking at ice crystal growth and nucleation and growth in ice cream, which is, of course, quite a complex material. And so you can see how the ice crystals would nucleate and grow. So they're like particulates here. You're looking at these ice crystals as particulates through a matrix. If you have any other questions, I'd be very happy to take them. Please do email me or on this address, or follow us on Twitter or LinkedIn, and we'd be delighted to hear from you. Thank you very much for your attention.
Carbon black is a pigment used in ink and must be dispersed with other ingredients into water, usually using a bead mill. For example, the conventional lab bead mill we used pumps material repeatedly around from a mixing chamber to a bead milling zone. When investigating ingredients or optimizing formulations, the many experiments use a lot of ingredients, produce a lot of waste, and take a lot of time. In contrast, Automaxion's mill can process multiple small samples in closed vials, increasing throughput and eliminating the need to clean a mill. The use of adapters and vials also dissipates the heat generated, and the samples can be exchanged quickly and stored in the same vials as used for processing. Though we want to increase throughput, we must measure particle size to compare how well each mill is performing. But rheology and stability is critical for inks and must also be studied. So when we compare particle size, we can see that the Automaxion mill consistently produces narrow distributions regardless of dispersion concentration. However, the recirculating bead mill generally shows a wider distribution and some agglomeration or unmilled material probably retained in the circulation system. This probably accounts for the zeta potential results where the Automaxion mill shows the effect of dispersant level alone. These two sets of graphs show how similar the rheology of the samples prepared with the Automaxion mill and recirculating bead mill are for two levels of dispersant. And these graphs show that samples of comparable stability over 4 weeks can be prepared with the mills. However, when considering the recirculating bead mill, preparation, pre-mixing, milling and cleaning takes more than half a working day for one sample. Although the milling cycle may be longer with the Automaxion mill, milling 3 or more samples and eliminating the cleaning more than compensates for this. So, in reality, over a working day, a recirculating bead mill enables only one sample to be prepared, whereas the Automaxion mill can process 8. These experiments show the Automaxion mill can rapidly make ink concentrates comparable with those using conventional recirculating bead mill and is useful for ink and other dispersion experiments. What it cannot do is process very viscous or shear thickening samples that cannot move within the vials. I would like to thank those mentioned here for their help, the RSC Formulation Science and Technology Interest Group for their organisation, and you for your interest and attention.
Thank you, everybody. I'm not seeing we've got any questions for the last 3 speakers. So if anyone has anything, if they would like to quickly type it in, I will be happy to field that for you. We do have a small amount of time, so if anyone would like to type any questions in now, I will be happy to field those for you.
Wait a minute. Stephen by South.
We'll give it another minute or so to see whether anyone's got any questions.
Dave Fairhurst here. I haven't had a chance to put a question on chat. Could I ask Stephen Bysart a quick question?
Yeah, sure.
Hi, Stephen. Thanks very much. Very interesting. A question, you mentioned you can't process very viscous materials. So I'm presuming in terms of pigment concentration, it's limited to fairly low concentrations or fairly well dispersed particles. Is that right? So what would be a sort of an ideal particle concentration that range that you could work in with your machine?
Well, to me, it's a bit more complicated than that because obviously it depends on the medium you're dispersing into as well. I really
I would say so. I'm looking because the work basically sort of ranges of normal solvents, you know, MEK, you know, things like that, NMP, DMF, just bog standard solvents with concentrations of particles of maybe that are well dispersed, say something like in the 5, 10, 15, 20% solids range. Could you? Is that?
I mean, I don't know the answer to your question, but what I would say that is, if it can flow, it will mill.
Okay. All right. Okay.
And sometimes even slightly thicker, because the problem is what you're trying to do with the planetary mill is couple the energy of the mill into the beads, and there's no physical connection.
Yes.
The smaller the beads get and the smaller the vial gets, the harder it becomes to couple that energy.
What sort of sample size are these vials?
I can work with vials from GC vials up to 100 milliliter vessels, and for milling, you only want to half fill them.
Okay. What's the smallest size you can do?
For this application, I would suggest a 10 mil sample in a 20 mil vial. Though, I mean, the mills are also used for co-crystal screening, and we go down to GC vials for that. Okay. And even I'm just 5 milligrams of sample. So
smashing, yeah. No, I'm thinking I typically use the scintillation type of vials.
Well, the vial I use generally is an EPA vial, what's called an EPA vial.
Okay, so all right.
27 millimeters diameter, and different heights give you different volumes.
Smashing. Thank you.
Okay.
Good. Once we've got you on, you've got Stephen on, we've got some more questions for you as well. What is the material construction of your vials? Are they expensive or are they cheap? Disposable?
That's one of the points of what I do is it's your vial. I don't care what the vial is. You tell me what you want to use. So for a catalyst application, we've used plastic vials. But usually it's glass. I mean, you also have to remember that you can't put in the vial something that will have too much momentum and will break a glass vial. So smaller beads or less heavy beads. If you go above, you know, if you put a big metal bead in there, the vial will smash if it's glass. Yeah. But of course it won't if it's plastic. So whatever you want.
Good. Good. Mm-hmm. There's a couple more questions coming really related to, say, temperature control. That is the temperature control, and what's the maximum temperature you could go to, and the viscosity limit.
Viscosity limit I just discussed. I don't know it. My principle is if it will flow, then it will.
It's measurable. Yep.
What was the other question? Sorry.
Temperature.
Temperature. There is no temperature control on the mill, but I've got one here. This is the block of aluminium, and it acts as a heat sink. So generally, you don't get excessive heating. If you want heating, of course, you could do the inverse and actually heat the block up as well. But there's no actual physical control of temperature.
And final question we had for you, are your mills scalable?
You mean if you run a sample in my mill, will it produce a similar result on a larger mill?
I presume that's what the question meant. It's one from a chat.
I have been told by a pharmaceutical company that they found that the results on my mills were scalable to a different process. But obviously, I mean, that's a huge, complicated question, depending what the mill is and what you're doing. So
exactly, and whether the situation is the same or not. Excellent. Well, thank you for that. Well, thank you to all my presenters for the last hour. We have a small.
Philip, sorry for
time
the
window.
interrupt.
Yep, sure.
Can I add to the answer given by Steve related to the question asked by David?
Yeah, sure.
Yeah, as you can see in this particular poster, you know, it's we tested it for carbon black pigments specifically, and there you can see that it's a particular grade of carbon black, as it has a surface area of around about 70 square meters per gram. And we could add up to like approximately 18% of this pigment in the formulation. So just adding on to that point by Steve, that as long as it flows, you know, you can mill it in the equipment.
Okay, thanks.
Yeah.
Well, yeah, thank you to everybody for the
Thanks, Ali.